Good morning, everyone. First of all, just present myself. I'm Afonso. I'm a volunteer here at PyCon. So if you have any questions, any technical issues, just follow me, ask me for anything. If I can help you, I'll do my best. Starting with the talks, I think you are eager for it. Just presenting the next talk from Lisbon to space by Marília, Simões and Nikki, Grens. Thank you.
Hello, everyone. Can you hear me well? Yeah? Okay, perfect. Well, first of all, thanks a lot for the invitation. It's really a pleasure to be here presenting our experience and our work and look at this talk as a sharing experience, okay? So even though we are a company, we are here to share our experience with you, and I think that's the main goal of a community, is that we can learn from each other and to share our experiences from all the projects that we've been doing, and especially in this case around space. So I'm Marília and she's Nikki. We are both from ML Analytics. I'm going to explain you who is ML Analytics. But then today we are going to talk from Lisbon to space, data science at exoplanetary scale with Python, of course. Okay, so first of all, as I don't know, excuse me, I don't know if everyone here is from the data science field. Is it? Who is from data science? Who is a data scientist? Okay, so I'm just going to give a brief introduction, very, very brief introduction of what is data science so that we all have a little bit of insights about the area, because then the rest of the talk will be somehow related with data science. So it's good that we have this background. Then a brief introduction, or I will try my best to be brief about ML analytics. And then we are going to jump and to fly into space. So we are going to show some of our space projects, focusing on ARIEL mission. That is a mission that's going to be launched in 2029, which we have been collaborating for the past years. And especially, of course, using machine learning in the ARIEL mission. We are going also to show you an app that we have developed as one of the projects for the mission, and some conclusions. So starting here with data science. Well, what is data science? I think everyone for sure heard about it, even though if you don't work with that. But at the end, in very short, is a discipline that puts together all different fields that use scientific methods, processes, algorithms, systems to extract knowledge and insights from structured and unstructured data. So at the end, what we want to work with data. So there's data everywhere, in all industries, in all companies, in the research, everywhere. But the fact is, we need to be able to work it the best way possible, of course, to take the insights and the knowledge that is hidden in the data. And so this by itself is a discipline, it's a science, and that's why it's called data science. And so just to give you an idea of how a data science works, so typically I brought here CRISP DM. I think this sound is a bit crazy. The CRISP DM is a methodology that is in place for many years. It's still since the time of data mining, that probably some of you have heard that term before. And basically, a project works as I mentioned. So in data science, we want to extract knowledge from the data. But first of all, we need to understand what is it about. So if it's business, if it's the research, what is the data about? So that we can, when we look into that, we can understand what the data means, what the variables mean. So that's one of, in our case, in our experience, one of the most important steps of a data science project. So it's the business understanding. Then, once you know more or less what is the business about, what is the research about, then you start working with data. So then you look into the data, you look into the variables, you clean the data as much as possible, you organize the data as much as possible, you create new features that could be relevant for the situation that you are working on. So imagine that if it's a bank regarding, for instance, loans, so you can create features that would somehow resemble what works and what is the situation that problem, that research question that you are investigating is about. You can support your algorithms with that. It's a little bit like a child. So whenever we have a child, we need to teach them, we need to educate them, right? And so we need to give them rules, we need to give them information regarding our context, our family. So here is the same. So you need to create your features in order to support your algorithms so that they can learn the best possible. And then it comes, finally, the modeling. So the models are very important, of course, but it's just one of the part of the project, okay? So then there are 1,000 algorithms, and I'm not going into that part. But once you create, you explore a certain model, you implement a model, then you evaluate, you test, you see in place, and if it's not okay, then you iterate. And it's always like a cycle. It takes a lot of time, and it's almost impossible that you have a good data science model and a good data science project in the first iterations. And then once you are comfortable, then you put it in production. Then there are other sides, that is the ML operations, where you have to monitor, you have to, 1,000 things that you need to put in place so that it can work in real time. Eventually, it can even retrain itself in real time as well, but one thing at a time. So this gives an idea of what is a data science project, and the part in the middle is to mention that it's called data science, it's a science. So when we are working with data science, we have to apply the scientific method. So we have a research question, we need to explore what is it about. We need to make questions, we need to prepare the data, again, to explore, we need to evaluate and formulate new questions. So again, it's again a cycle, and that's why it's called data science. So to be a good data scientist, you need to also have this science profile somehow. So you need to be curious, you need to go after the information that you want to explore. Okay, but this is to give an idea, and then here I like a lot this graph that goes, let's say, in stages of the projects in terms of analytics that you can do. So you usually start with the descriptive analytics, so that is to show what has happened, and then you move forward to the diagnostic analytics. So why did it happen? And then you try to predict. So what will happen based on the information that you already have, based on the patterns that you already found. And then the prescriptive part. Okay, now that I know, now that I have all this information, now that I have different models, can I start doing simulations? Can I start doing optimizations of my business, of my projects that I'm working on? And so these are the areas, the techniques, the fields that belong to each one of these layers here. Okay, so I think this set more or less the scene of what is data science, I hope. And so now to talk a little bit about ML analytics. So ML analytics is a boutique. We like to call it a boutique. And why do we call it a boutique? Because we like to develop projects tailor-made to the needs of the clients, of the research, of whatever we are working on. So we don't have a product that we go to a company and we put the product in the company. We do the other way around. We talk with the clients, we understand what are the needs, and then we go to the state of the art if needed. We even develop new technologies if needed, and we bring it to the client's situation. So it's the other way around. And so the way that the clients look at us, it's not that we are a provider, but we are a partner. And why did we create this? So I'm the co-founder, one of the co-founders of the company. And why did we create the company? So this is a family company. I like to joke that this is the first family business, data science family company in Portugal, because it's founded by myself and my husband, Luis, which is, standing on the right side. And we created this company in 2017, after we have been in the Netherlands for 7 years. So we are both from the data science field. So I'm from mathematics, applied mathematics, and he is from computer engineering, but both with more speciality in the data science world. But he went to the research, and I went to the business in our early ages, let's say. And so while in the Netherlands, I worked for TomTom. You remember TomTom, the GPS company? So I had the team of data scientists at TomTom, where we were like an internal consultants providing insights from the data, like customer behavior, different information that you can imagine, to different departments of TomTom at that time. And while I was working there, at a certain moment, then I was invited also to run a business. So I was at some point working a lot for the maps. So we remember that once in a while you had to update the maps. And then they invited me to be the one running the business itself. And then I moved to FedEx, so the logistics company, but there to develop, to the business development, to help them developing new business based on the data they have. While I was doing this, Luis was at European Space Agency, so he had already developed projects for European Space Agency from Portugal, but then he applied and it took a year, but he managed to go to European Space Agency to Advanced Concepts team, where they explore different techniques, new techniques, and mainly AI, to the space industry. And then they would see the things that would work better, the things that would not work so well, and then eventually it could go into the missions. And so that's why, with both knowledge, so one a little bit more to the business, another one for the research, at some point, after 7 years in the Netherlands, we said, well, it's great to be here, I love the Netherlands, but we had already a child, and it was time to come to more close to the family. And when we came to Portugal, we didn't have the idea to create a company, but actually there was this hype of data science at that time, which was not there in 2010. So a company in 2010, understanding that they want some mathematics in a company, no one understand why and what the mathematics would help them. And so because we saw that there was this opportunity, and we had to, of course, to see what to do next. And so we decided to create this company. But then it was our company. It was not working to anyone. We were running the business and doing the things the way we saw for a year. That was, okay, well, let me move away. Can you hear? Yeah. And so we really are passionate about data. And so we created this company to really help the clients and the companies to do the best out of their data. And so that's why we like to say that we are ML Analytics, which is turn your data into business or turn your data into research, whatever you, you like. And so as we are both from business and from research, we have these two areas. We have the area of the business, so we have services, but also we have research. So now today we are going to talk about the research part, okay? So we are now actually 12, but we are 13. So I tried to make a small team, but I'll talk about that a little bit later. And we have projects for different industries. So there is space, there is telco, there is pharma, finance, media, energy, logistics, and so on. At the moment, someone mentioned, well, but you need to focus in an industry if you want to succeed. And I said, okay, good, but can you tell me which industry? Because they're everywhere. Or you need to have a product. Okay, but can you tell me which product is the most, well, if I do in my project the business understanding, now I need to do the market understanding as well. And so that's what we have been doing in these first years. But okay, aside from that, this just to mention that we have models in production for many years. So we have experience in putting them in production and to see what really doesn't work and what are the main struggles to have a machine learning model in production in a business. Aside from that, we are recognized as an R&D entity in Portugal. I think it's also nice to mention. And, well, we ranked nice in the scoring in there. Okay, so next. So then there is this idea, okay, we need to build a team. And how do we build a team that would work with across industries and for the different type of projects? And so the main part that is very important to mention is that we don't need a large team. We need the good team and we need the right people. So I see each element as a piece of a puzzle. And somehow they need to connect, they need to merge, because at the end, it's the team that will develop the good work. And it's the team that is there if it will do a good job, if everyone will enjoy and appreciate what they are doing, because it's when they really put their attention. And as I mentioned, to be a good data scientist, you need to be scientists. You are the one that are defining the question. So no one is going to tell you, now you need to do this and that and that. Well, you can have a guidance, but you need to be the one doing the job, let's say. And so it's important to, when we select people, it's not only the technical part, but a lot from the social as well. So because the team need to fit. Then the fact that we are exposed to, and the team is exposed with different industries, also helps to build a deep toolkit of problem-solving techniques, because the problems are, of course, different. There are some that are somehow similar. Most of them are different from different industries. And, of course, domain knowledge is always crucial. So we need to have someone, again, help us understanding what the data means, but the data is data. So it's important to have a versatile data team that could tackle the problems from different domains. Well, what does it mean, sharing a little bit our experience, what does it mean to be a boutique of data science company in Portugal and who works with clients like ESA? Well, we need to be focused and we need to be agile. So a boutique of data science, we need to offer highly specialized, flexible solutions able to deep dive into clients' challenges and build long-term partnerships, because at the end, we are going to be part of the teams of the clients. Space-ready mindset. So years of solving messy, uncertain, real-world problems combined with dedicated AI research for space prepared us to contribute meaningfully to missions like ARIEL, that we are going to talk about today. Global impact from a local base. So we are a small team based in Portugal, but we've led projects globally and we have missions, but we also have clients worldwide, like in the Netherlands, for instance. Reputation built through execution at ESA didn't come from building branding or scale. It came from years of delivering technically sound production-grade AI solutions, including the space domain. Well, at the end, what does it mean is like, it's from the experience and from the dedications that you create a good CV and you create good work. So this is the main takeaway that I want to bring here with this whole conversation, is that small teams, quiet work, global missions. You don't need a big branding to reach the stars. You just need to have great work, okay? So now, ready to fly to space? Some examples of projects that we are going to bring here. Well, this was the first project that actually we worked on. It's about intelligence planetary site selection. What is this about? This was a software to pilot for autonomous landing spacecrafts onto planetary bodies with hazard detection and avoidance. What does it mean? So it means that when you launch, you have a mission, you want to launch a satellite somewhere. A satellite? No, in this case, you remember the Mars, where there was this rover landing in a planet. So basically, it's like if you want to, usually you launch like a cannon. So it just, wherever it lands, and that's it. But of course, there are criteria. I think in English that's the way to say. So criteria. And if it lands on the site and if it turns, then the mission is gone. So it's very crucial to also try to understand in which area it will land so that the mission would follow, right? And so here it's a software, an algorithm that in real time, while it is descending, it would analyze, so you see different sensors there, so different information, and would, with information from those sensors, it would select the best place to land, but the decision is made while it's descending, so it's in real time. So this was a project very interesting. It was supposed to be used for landing on the moon. Unfortunately, after 5 years it decided to cancel the mission, but now ESA is again looking into the software to use in different missions. But so this to say that even though it was designed for space for this specific problem, this real-time multi-decision type of algorithms can be used in different situations where there's the need to do a decision-making while in real time, while the thing is happening. So it's also important that technologies we develop, we see to also, let's say, different types of problems. Then this is another one. Maybe can you put the video? Yeah. So this is a different one. This is an interesting satellite swarm control. So this was the neural network for autonomous formation flying in zero gravity to create a precise triangular formation. So basically the idea is that you have, in this case it was these 3 robots, but it could be satellites. And basically they need to somehow connect without a central source of intelligence, and they would need to align themselves into the certain shape, in this case in a triangular formation. So these are the robots that were in ISS to make the experiment in there. And it was very interesting. But at that time, this was a project done while Luís was at the European Space Agency, and no one actually knew if this would be useful somehow, someday. And now it's very interesting to see that there is this LISA mission that is going to be launched, if everything goes well, in 2035, where actually they will need, they are going to explore the detection of gravitational waves. And they want to actually have 3 satellites that will be somehow connected to explore the gravitational waves. So this is nice when you see that actually a crazy idea that actually ended up being explored and tested in ISS. Actually, didn't, but almost tested, because all of a sudden at the end, again, there was a problem somewhere and it was not tested, but it was there. At least we have the picture. But now it's good to see that this technology is actually going to be useful. Not sure if it will be this specific one, but the idea, it's going to be used in a mission that's going to be launched in 2035. Another one, if this moves. Maybe you need to do it there because of the video. Yeah. So this is another one. So this is from ESOC, so it's the ESA Operations Center in Germany. And in this case, what they wanted to, so what they brought to the Frontier Development Lab, which is a NASA and ESA research accelerator, they brought a problem there while Luís was working in there, and then we completed the project at ML Analytics. But there they also developed a prototype, and the idea was that there is this cluster of satellites that was that is there collecting some information, and once in a while they need to connect to the antennas in the ground in order to send the data that it's collecting, because sometimes the buffer is full and they need to send the data down. And so there's someone that humans that were creating these schedules. So from the different satellites, depending on the place where they were in orbit, and the place, depending on the place where the antennas in the ground were located. And so they had to schedule, to make the scheduling, to say, okay, at this moment, at this time, this is the moment that the data is coming down. But the fact is that it was done by humans, and so the challenge was, okay, let's make algorithms to make optimization and to put this, let's say, more automated. And so we worked on this project. And again, for us, and especially in space, and coming back to the information that we were talking before, well, if I'm working for a bank, I more or less know, because I go to the banks and I know how more or less the business works. If I'm working for telco, I more or less know how the things works. But when we work for space, the business understanding is very difficult, because it's not something that we have on our day-to-day life. And so it's, okay, there were antennas, and there was one that was called VIL2. Okay, nice. We are months working with that. Okay, nice. It's a VIL2, and the VIL2 will send the data at some point. But eventually, we went to ESAC in Madrid, ESA center in Madrid, and Luís told me, well, you know, Marília, you see that antenna in there? That is VIL2. And I was like, what? You know, it's like all of a sudden we saw something that was only in the computer, we saw it there, that was VIL2. And when I looked, actually, it was turning to grab the data. So you cannot imagine how I was surprised and happy to see actually working. So it's in front of me. It's not something that it's somewhere in space. It's actually here. So this to say that it's also very important. And if possible, whenever you are working on your project, if it's not a data science project, any other type of project, it's so nice when we see the connection with what we are doing actually implemented in the business, in the real world, let's say. So I really advise you, even if you don't have the need to, but once in a while, it's good that you try to connect with what you are building, because it makes a complete difference. After that, when I was looking to the data, I was like, okay, now I know what is happening. The type of information is the same, right? But at the end, I saw it. I didn't see the data coming, of course, but I saw the VIL2 actually turning. And for me, it was really, really interesting. Okay, and now we jump into the ARIEL itself. I hope that you are space enthusiasts, because it's a little bit about space, as you can see. Okay, ARIEL. Well, I think giving a little bit the background. So imagine that you are in 1990, and if you at school, everyone was told, okay, what are the planets that we know? And so the kids learned to say all the names, and even Pluto, which is not now in the list, but even Pluto, by then was considered a planet. But now, actually, there's known more than 5,000 planets today, and actually it's growing. Okay, so now there's this idea that every star now is expected to have planets around it. So you can imagine how many planets are there. And so if we were from the previous one, if we zoom in, we saw, all of this. But imagine you saw that red one very little in the middle. So imagine that we zoom into that one. And what we see. Actually, I don't know if you are a fan of Star Wars, but remember that there was this planet that was the lava planet. The floor was lava, like the kids say today, the floor is lava. So actually, there is the K2 141b exoplanet that is like that. And so scientists have found this exoplanet of molten lava oceans where they forecast supersonic winds and rocky rain. So this actually exists, or at least something similar, okay? And so the fact is there are new scientific questions arising. And for instance, why the solar system is as it is, what are exoplanets made of, what are the weather like there, why are they so diverse, how did they form, how are they habitable? So there are many questions that are coming more and more, and so there are many missions now, more missions, let's say not many, but more missions, to study exoplanets, and ARIEL is one of them. And ARIEL, basically, the main goal of ARIEL is to study the atmospheres of exoplanets, but making like a census, like we do the census in the population. So now they want to do a census of around 1,000 exoplanets regarding their atmosphere. And so that's the mission that we are going to talk about. Can you put the video? So they are building a telescope. Actually, the hardware, that's interesting because part of this hardware is built in Portugal as well. And we are supporting the machine learning part of the mission. So I'm very proud that this is like the AI and the hardware mission where Portugal has quite a lot of influence. Of course, we have influence in others, but for me, this is a special one because it's where I'm in, right? So this is the satellite. So this is just to say that actually what this mission is going to do, Nikki is going to show it. But at the end, it's a telescope that is pointing to a certain star, and it's always analyzing the light curve. And whenever there is a planet passing by, it will try to understand if that was a planet and more information, but we will show you about that later. Can you move? Okay, so why did we come to work with this mission? So because in 2021, yes, Luís participated in a worldwide competition that was launched by European Space Agency, especially for this mission, because they saw that there is this type of data that is so noisy and is indeed so many that they ask for help for the scientific community to support them, AI scientific community, let's say, to support them on dealing with this data. And so it was a competition that I think was around 3, 4, 5 months, I'm not sure. But the fact is that it was very hard, but Luís managed to be the top of this competition with a very considerable distance to the second place. And so he was invited to give talks, to explain the way he had developed, and then they were very happy with what they seen, and they invited us to be part of the consortium meeting to support the machine learning part of the mission. So that's why we are part of this mission, and we are there since 2022. And so this mission has 2 consortium meetings every year. And last year it was interesting because last year the second one was here in Portugal, no Pavilhão do Conhecimento, like the Science Museum. And we were together with the astrophysical and the science faculty. We were one of the organizers, and so you can see the white part on the right side of the picture is ML analytics supporting the organization. But it's a very very interesting mission. So now we go a little bit more into the details, and Nikki who is our one of the data scientists that is part of the team, is going to explain you more about it. Maybe you need to come.
Yes. Thank you. Can you hear me? So as mentioned, ARIEL will perform a chemical census of 1,000 exoplanets. And what do they want to do with this? They want to know the chemistry of the atmosphere, but also the temperature, the cloud coverage, the wind speeds and climate. So they really want to get to know the atmosphere a lot better. And how will they do this? So they will look at when a planet is transiting, so passing in front of the star. So if you look at the animation, when this is happening, there is a dip in brightness. So part of the brightness is being blocked by the exoplanet. But also, part of this starlight is going through the atmosphere of that exoplanet. So this is around 1 photon in 100,000 photons. And that one photon will then give us information about the atmosphere of the planet. So what is happening, if you look at the top figure, when the starlight is passing through the atmosphere, part of it is being absorbed by the different molecules and components in there. And then it's being absorbed at different intensities per wavelength. And that difference will then give us information about the chemical composition. So this is an example of measurement by the James Webb Space Telescope. And if you can see, there's a small difference in absorption of the green wavelength represented there and of the red one. And that small difference was enough for us to be able to say, okay, there's carbon dioxide in there. And this is quite a simple example, but there are exoplanets where we can tell way more information about it. But nowadays from Earth, we only have a few tenths of it where we have a detailed characterization. So like this one was 107b, where they can say, for example, that there's water, carbon dioxide, but also ammonia, and so on and so forth. But with ARIEL, we want to be able to do this for 1,000 exoplanets. And this is a really complex problem, and scientists have acknowledged that without AI, this is quite a difficult, almost impossible challenge to solve. And then, for example, this is the one of our Earth. So why is this important? Because also one of the questions, is there life on those planets? And from the one from Earth, we see the ozone, carbon dioxide, and water as expected. But we also see methane. And with this composition and quantities of the different molecules, methane is actually a biosignature. So it would show, for example, if you would be looking at us from another planet, that there's life in here. And in our case, methane comes mainly from the cows. So it is interesting to, from just this picture, that other people outside of our planet would be able to see, oh, there's something in here. But from the examples I showed before, the light curves, so that the light curves is the curve of brightness over time, they look quite clean. But in reality, they're quite messy. And if a star, for example, has multiple planets, then there are different dips and different intensities. So it can be quite complicated to really focus on one light curve and on to get the clean data. But so why is it so hard to measure this? Because there are a lot of noise sources, including, for example, the instrument, because the instrument is not quiet, so there's also noise there, or the noise coming from the photons itself, but also from stellar spots. And stellar spots are places in the star that are cooler, so they're darker, and that means that they also give out less brightness. So if we see in the example of the bottom right figure, there is a picture of the sun and its stellar spots and a comparison of how Earth would look like in comparison to it. So it is quite a challenging problem with different noise sources, where the dip itself is also quite small because the planets are really small compared to the star. And it is a challenge where AI and ML will be used. So if we look at this, you don't need to go into detail, but this is the data processing pipeline for this mission. So all the steps involved, from going to the ARIEL and to getting the data the scientists need. So it's quite complex. And today we will focus on one of the contributions that is being made through AI and ML in this problem, namely going from the light curves, so that's the bottom middle figure, to the exoplanet spectra. So the transmission spectra I showed before. And just to highlight how ML and including us, are helping in this mission. There's first a concept of science, so we need to know where ML could actually be useful and be used in. But also the concept of operations. So we need to make sure that once the models are made and are being used, that the performance is good. That, for example, the model is not hallucinating a certain chemical composition there, like ChatGPT sometimes does. So it is really important to have safe operations. So that's also another step where ML is being used. But for this problem, we want to, given the light curves, on the left, get the transmission spectra. And we are building a model to do so. And for now, we have a lot of simulated data based on experiments scientists ran with information of the stars and the exoplanets and the chemical composition. So for now, we know the true transmission spectrum. But once this mission is deployed and the model is being used, we don't know the true transmission spectrum. So at that point, we need to make sure that the output of the models are correct and can be used for science. Yes, so I don't know if many of you know what machine learning is, so I'll just quickly go over it. So then, as I mentioned, we have now simulated inputs and output pairs. We give it to the machine, to the ML algorithm, and then the algorithm learns by itself patterns in it, and then generates a model. And then the model will be, to the model we will be giving inputs to then get the outputs. In our case, for the example that I'm going to be showing now, we used a really simple neural network, which is quite fast to train. And for the application that I'm showing, that's quite important time-wise. So for this task, we developed an application. This is an educational application, and with the goal of showing to the community, to students, to scientists, what is happening here, and to anyone that's actually curious about exoplanets and AI. So I'll be going into it. And in this app, so if you want to play with it after this presentation or in your free time, you can do so. It's online. And in this app, the only thing you can do is change the data pre-processing pipeline. So the model is set, and the only thing that will make a difference between good scores and bad scores is how you pre-process the data pipeline. And first things first, here at the top, you can select a few exoplanets. Oh, I'll use. And remember, we talked about the one with the lava? It's actually also here. It's this one. So, but if we look at the raw data, we see that, I mean, I cannot make anything out of it. So I don't know if you can, but it's quite noisy and messy and everything. And in case you're curious about the exoplanet itself, you can go to these different links. For example, this is of the site of NASA, where they have a simulation of the planet. You can see the solar system there. So in case you're curious about exoplanets itself, there are a lot of information here. But as we can see, this data is quite noisy. So on the right, we have a lot of different pre-processing options. And I'll quickly go over them in case you want to play with it later. So the first is the window radius. And what does this mean? It means that every point is being aggregated with this radius of points before and after. So if we do this, we already, we start seeing that the dip in there. And if we do more, we see it better. But I mean, what is the optimum of aggregating the data? Because the more you aggregate, the more information you're losing. So it's something you can think about it. Then we also have simulations of different transits, so different times the planet is passing in front of it. So you could aggregate over number of transits. So if the more you do, the cleaner it is. But again, a question, what is wise, what is not? Then I mentioned about aggregation, so there are different aggregation operators. And if you look at it, this link is to the Wikipedia page to mention a bit about the generalized mean and what this different p's mean. You could also use symmetry. And why is symmetry important? Because in an ideal world, the star would be evenly bright everywhere, and during transit, this would be a symmetric dip in light. But because of stellar spots and noise and everything, we know that that's not the case. So if we use symmetry, we could aggregate the points across the middle line to try to reduce this effect of stellar spots or noise at that moment. So symmetry can also be used, and if you can see then, this one looks quite weird, but if we use symmetry, that effect is even out a bit, not entirely, but even out a bit. So these first 4 parameters are of the data aggregation options. So how do we want to aggregate the data to go from, as the start, we had really noisy data to something we can analyze and see, oh, okay, there's something happening here. And then also, we don't want to give all the points to the machine learning model, because then you're giving too much data and it cannot really learn detailed connections and it's overfitting, so that's not good. So there's also an option to select the feature grid. So how many or which points we will give to the model, and I'll show you which ones it's giving now. So if we have, this one is how many points are being given, so 25, and because symmetry is applied, it only looks at one side. If symmetry is not applied, it looks at both sides. So we have the 25 or more, or not 25 is the maximum and less than 25. And then you also have the spacing between the points. Is it more important to give fewer points with a bigger spacing between them, or more points with a smaller spacing between them? And then these are the predictions of the model. So then if we give out, let's say we use these applications, we we try to train the model, we build an AI, and we see the score. The maximum score possible is 10,000, but in this application, due to the simplified model, it goes around less than that. I don't really exactly know the number, but so in general, if you're interested, you could try to play out with the settings and see which one gives a better option. Also, something interesting to notice is that for this particular lava exoplanet, we're doing quite well, but then that means that there are for others that we are not getting that good of results. So if you're interested, you can build your own model. There's also a leaderboard, not for this event, but with the leaderboard, you can see what other teams did and try to compete against them and see if you can do better than them. And if you go to this page, if you're interested in the science behind it, there's a detailed explanation of it. But this app was built via analytics so that the community could learn from it and play with it. And you think, oh, easy, right? Well, not really, because of the 6 different settings, there are more than 1.5 million possible combinations of parameters. So that's quite an extensive possible set. And if we wanted to analyze them all in detail, that would not be possible. So this project also falls into the category of citizen science. So with this, we wanted to not only give the community the opportunity to learn about this project, but also involve the community and let them help us and analyze different setups. So what is citizen science in short is having non-scientists and outside community help with the data analysis or classification or different tasks in different projects, so that then with those results, scientists can perform more science. So this is an example, but there are others, including Galaxy Zoo, which asks the user to classify galaxies based on its shape, or Folded, which was it's a game where you look into the protein folding structure. So there are many of these. And if you're interested in it, Zooniverse is a platform which has multiple of these citizen science projects in there.
Okay, so one way and why we built this app is actually to share with the scientific community, but also with more, let's say, not related with science people, so that they could also be involved in these type of problems and be able to deal with this data. And actually, the first challenge that was given to us and where we built this was actually for a hackathon, a first hackathon that we created. But it was, when someone mentioned this to me, I said, well, that's impossible. But it was a very nice surprise, because it was for kids from high school. And so they were 16, 17 years old. And when we explained what they were doing and that somehow they were actually contributing to the mission, you cannot imagine these kids that most of the time they just want to look at the phone and do not pay attention to many things, let's put it this way. You cannot imagine how they compete against each other. They were actually asking questions, They were very interested in what they were doing, and they were really asking, but is this real? Are we actually dealing with the data that is also being used for the mission? And they were like, yes, that's it. And you cannot imagine how excited, of course, not all of them, not the 50 or I don't know how many they were, but many of them were. And actually there was one kid that asked us if he could come to our office for a day because he was in this period of selecting the university course that he wanted to pursue, to follow. And he asked if he could come to work with us for a day to see if this would be actually something that he wanted to go. And I think he went for this. He's applying for that at least. But this to mention that the goal of building this app, and we made it somehow simple, was actually to share this information, to share this knowledge, and to put space more close to the community, let's say. And so that's why we also bring it here. So imagine that you want to do some hackathon with someone with this type of application. It's free. You can use it. Just contact us. We can create a leaderboard for you, and it can happen. And so it was really nice because at the end, these kids were presenting the solutions after 3 hours of dealing with the tool and with the data. And it was really nice to see kids like, I don't know, 16 years old, mentioning, well, we used harmonic mean because it was the one that gave the best results. So I'm very keen about using harmonic mean. And we were like, well, it was the first time that you heard about harmonic mean, almost. But it's good, to bring these insights and this knowledge also to kids. Not only to kids, then also we did another, this is still from the same hackathon. And this was actually the leaderboard of these teams. And we can see that after an hour, more or less, most of the teams were already reaching the highest score possible in there. And then we also did another one, but now in this case it was at ESAC, so at ESA in Madrid. It's the European Space Astronomy Center. And it was aimed for university students with programming challenges, not only the tool. The tool was, again, to get to know with the data, to get to know with the problem. And it was also very, very interesting, the results in there.
Yes. So then, as we mentioned, we asked kids or people from universities, community in general, to give out answers. But you might be wondering, what was their performance and how did they do? So if we look at the graph, we see that after around 80 submissions, a lot of them already were at close to the optimal solution. And I want to give a disclaimer, this is what we, based on the problem and on the data and knowledge, what we think is the optimal solution, and no one has found a setting that has a better solution. But because there are many possibilities, it might be that there's also another one that gives good results. But for now, we believe that this is the optimal solution in terms of the scoring function we have. And we see that if we look at the median, after around 50 trials, a lot of them were ready with good solutions. But you might be asking, oh, why don't you give a machine or an algorithm? Why don't you let Python itself solve this? And we did that. But before going into results, do you think Python is better or worse than humans at this problem? If you think Python and the machine itself is better, please raise your hand.
This was the Optuna model.
Okay, I see a few hands. Well, wrong one. So when looking at, when using Optuna, and Optuna is a Python package for hyperparameter optimization. So in this is in machine learning, you want to optimize the parameters being analyzed. But this is a package that can be used for any other problems where there are parameters you want to optimize. If you have a goal, a scoring function, or something you want to optimize in parameters, you can use this. And it works quite well. It's the state of the art. But for Optuna, it took it longer to get good results. So it took Optuna longer to go to the optimal solution. And some of them converging even to less good solutions. But if we look at the median performance, we see that at the start, humans perform similarly to the machine. But then, because they have a feel of what is happening, they go faster to good results. So at that point, they're better. And only at the end, once the machine has looked more extensively at the parameter space, then it performs better, so Optuna. But it is quite interesting to see that for this problem, because humans get a feel of what they're doing, they much faster go to good solutions. So that was an interesting finding. And since we have so many results, we also wanted to analyze them and see if we could get some insight out of it. So to do so, we used TSNE, so you can also apply this using Python. And this is a technique that, from, in our case, a 6-dimensional space, it reduces this dimensionality and it projects the different points to a 2D visualization. And something important is that points that are close in the 6-dimensional will remain close in the 2-dimensional, and points that are far in the 6-dimensional will remain far in the 2-dimensional. So it's a technique that you can use to then analyze the results you have, because yes, we have a lot of data, but if we don't do anything with it, if we don't get meaningful results from it, then we have it for nothing. It's interesting to notice that up to now, from the 1.5 million possibilities, around 2,095 have been selected out of 3,000 submissions. So there's still a lot of options to be analyzed. But then if we look at this graph, so then you project the 6 dimensions to the 2 dimensions, and then you paint different dots based on either scoring metric or parameter. And if we look at scoring metrics, it was really interesting to see that on the right figure, you have the cluster that has the best performing setups in terms of the scoring metric in the app. But in the middle, you have the cluster of the best performing metrics with respect to another error metric, which is the mean absolute error. And because people could visually see what was happening, they also explored other spaces that were performing well in terms of visually, but maybe not necessarily in terms of the score. And because of this exploration of this other cluster of points, we actually managed to find another setup that was working best in terms of other metrics, and I even used it during my master research. So this actually gave us some useful insights and something we continued working on. And then if you look at this is the space painted by the different parameters that I showed in the app. And something interesting is that top left part of each graph, you see that there's some space that has extensively been explored. And from this analysis, we know it's because they really explored the combination of number of points in the feature grid and the spacing between them. So you can see on the last two figures the color pattern in there. So that was interesting, so that people, based on one setup that was working well, they really explored the different options of features, number of features and spacing between them. So this was a lot of talking about what is happening, but since this is also a technical audience, we decided to bring the architecture of what is happening here, because believe it or not, this was all based on Python. The entire app, we didn't need to any other programming language or anything. Streamlit was what we used for the front end, and that is a Python framework that allows data scientists like us to show interactive apps. So in case you haven't and you would like an interactive app, it is quite easy to learn, and it works well, so we strongly recommend it. We have also been using it for other projects after this. But then if you look at it, what is happening there is basically that you have the user interface components, so the different, the sidebar where you can control the different parameters, also select the different planets you want to see. And then there's a state management, which takes care of the parameters you're inputting and of the logic that is happening. So if you want to get the score of your model, then it connects to the API communication, and this will then communicate with the back end. And then after receiving from the back end all the information needed, it will do the visualization and for example, the leaderboard or the plots itself with the scores and so on. So this is the front end. And then if we go to the back end, we used Flask REST API backend. And here, when the user says, oh, give me my score, then we go here. And what is happening here is the entire, I don't know if you can see it, but it's the entire logic of the machine learning, so the data pre-processing, the training the model, doing cross-validation, and then doing the scoring functions and metrics in the game, so the game logic. So these are all the different steps in there. And then once the different Python codes have been run with the code that we are also using for the project and not just for the app, then this backend communicates again with the front end and gives the results, and then the user can see the visualization. So this was all possible due to Python. So if we look at everything, we used, for example, Python, Jupyter Notebooks, Pandas, Scikit-learn, Docker, GitHub, Streamlit, I was mentioning, we strongly recommend it, Flask, Request, Matplotlib, Seaborn, Optuna, and Cloud Azure. So, and this brings me to the end of my part. Thank you very much.
And also the presentation. So, takeaway messages that we want to bring here. So the most advanced science can rely on the same open source libraries that many of us uses every day because they are so good. Python is an ideal language for curiosity, rapid prototyping and iteration, but also for production-grade software. But stay curious, share what you built, and don't underestimate where Python can take you. Sometimes the sky is not the limit. And do you want to help? Do you want also to participate and collaborate to this mission? So now there's another data challenge open, like the one that we participated in 2021, where it's in Kaggle platform, and it's connected with NeurIPS, which is the biggest artificial intelligence conference in world. And actually there's a prize of $50,000, I think. Cumulative. Well, then you explore the details, I don't know. But there's this competition open in case you want to participate. And, well, the Astrolab gave away to the telescope, but the same ingenuity still gazes at the stars in search of new worlds. So, thank you very much, and I hope you enjoyed.